Welcome back, class. In our next and final unit of the year, we are going to be talking about solid geometry, which some people will refer to as three-dimensional geometry. We're going to be looking at a variety of different polyhedron and a variety of different formulas as we start working with these. So I wanted to start with some basic definitions. Today, or in these next few weeks, we're going to talk about prisms, cylinders, pyramids, and cones specifically. A prism is formed by two congruent, parallel, polygonal faces that are called the bases of the prism. These are connected by faces that are parallelograms. So as we look at this example right over here, we can see that at the top and the bottom, we have these triangular surfaces. Each of these triangles are congruent. You can also see that they are parallel to each other, and these are what we refer to as the bases. Then, if you look at what connects those bases, you can see that there are these three rectangular shapes. There's one here, and there is one on the side here connecting, and then there's a third one right here. And although I referred to these as rectangles, it is important to remember that a parallelogram does include things like rectangles and squares if you think back to your to a lot of our definitions from earlier. Now, a cylinder, going back to some definitions, a cylinder is formed by two congruent and parallel circular bases and a curved surface that connects those bases. Now we're going to come back and talk about that curved surface later, but one of the things that I do want to point out is that in a cylinder the bases are circles, and remember that circles are not polygons, since polygons have to have vertices and circles do not. Okay, then we have a pyramid. A pyramid is formed by having one, and I do want to emphasize that, a pyramid only has one polygonal base. Okay, just emphasize that. And then it has triangular faces. Triangular faces that all meet at a common point called the vertex. So if you look at a pyramid, you're going to be looking for this one base. It can be any shape. This one happens to be a triangle. And then you'll notice that all of the other surfaces are also going to be triangular shapes. So we have this one, we have this triangle here, and then we actually have another triangle in the front, this one right here. So all of the faces are still triangles, and then they all meet at this one point called the vertex. A cone is formed by having a circular base. And again, remember that a circle is not considered a polygon. And then again, there's that curved surface that connects the base to a point at the top called the vertex. Okay, as we talk about these three-dimensional figures, we often refer to the faces, the edges, and the vertices. So the faces are basically all of the flat surfaces on the figure. These faces can be polygons, they can be circles, they can be hexagons, octagons, anything. The edges are where the faces meet. Okay, these are going to be line segments. For example, here is an edge right here. Here is an edge right here. Okay, the vertices are points where the edges meet. Okay, so in the diagram over here, this would be a vertice. Down here would be another vertex. Over here would be another vertex. So when we're talking about the different parts of the three-dimensional figures, you're going to hear us mention vertices, edges, and faces. Now, I wanted to give you a quick definition of what is a polyhedron. A polyhedron is a closed three-dimensional figure that's formed by four or more polygons that intersect only at their edges. Now, I do want to emphasize the word polygons. So as we look at these next couple of examples, it says that we want to name the following three-dimensional shapes and then decide, is that actually a polyhedron? Remember, to be a polyhedron, the surfaces have to be polygons, and we've kind of mentioned that a couple of times, okay? Let's start with this first one. When we are naming the three-dimensional figures, you always name it according to what shape is the base. So when you first look at this figure, what you need to decide is, where's the base of this figure? The base does not have to be at the bottom. Okay, it can be, but it does not have to be at the bottom of the figure. What you're looking for with the base is the two congruent parallel surfaces. So as we look at this figure, we can see that if I look at the bottom, there is this rectangle down here at the bottom, right? But there is no rectangle at the top that is parallel and congruent to that one. That means that the rectangle is not the base. In fact, the base of this is actually going to be this triangle off to the side, because across from it, parallel to it, is another matching triangle. And because the base is a triangle, we call this a triangular prism. Okay, if you look at the next one, we're looking for something that is going to have a matching parallel and congruent surface. And even though it's in the background and you can't really see it too well, there is going to be that circular surface. Okay, anytime the base is a circle, this is what we're going to call the cylinder. Okay, when you look at this next one, you're going to notice that all of these sides come up to this point at the top. Anytime all of those faces meet at one point, we know right away that this is a pyramid. To name this pyramid, we're going to have to go down here and look at the base and count up the number of sides. So since this base has 6 sides, we would call this a hexagon. And so we would refer to this as a hexagonal pyramid. And then the last figure, once again, we see everything meets at this one point, this vertex. So look across from that vertex. Here's our base. If our base is a circle, this one is then called a cone. Now, it does say decide whether each of these is a polyhedron. And we said that a polyhedron has to be made of polygons. So the only two here that would not be considered polyhedrons are the cylinder and the cone, and that's because circles are not polygons. Circles, cones and cylinders do fall often into the same category of three-dimensional shapes, but by definition, we technically cannot call these polyhedron. Okay, it did talk about counting the vertices, faces, and edges. We're going to come back and do that with some other examples. Okay, actually right down here. So as we look at a couple of these, I do want you guys to be able to identify how many vertices and edges and faces and bases there might be. So if we look at this first one and start with the vertices, there's always this one vertex at the top on a pyramid, but remember that a vertex is anywhere that the edges meet. So technically there's 1, 2, 3, 4, 5 more vertices down here along the base. That gives us a total of 6 vertices. As for edges, we're looking for anywhere where the surfaces meet. So we have 1 edge, 2 edges, 3, 4, 5. And then we have the edges along the bottom, 6, 7, 8, 9, 10. So this one has 10 edges. As for faces and bases, now sometimes we kind of lump these together and simply call them the surfaces. This one does kind of separate them. There's technically only one base on a pyramid, and that is the one at the bottom. In terms of the faces, there are the 1, 2, 3, 4, 5 faces along the sides. Remember that in a pyramid, these faces are triangles. So you'll notice that there are 5 triangles meeting at that vertex. And in this one, the base happens to be a pentagon with 5 sides. But the total of these flat surfaces would be a total of 6. Okay, if we look at the second example, this one is a prism. And again, when we're naming this prism, don't necessarily look at the bottom in all cases. Okay, if I look at the bottom, I can see down here what's either a rectangle or a square. But if I look straight up at the top, there is no matching congruent rectangle or square that is parallel to it, which means that this is not the base, even though it's at the bottom. What we need to look for is this pentagon, and we can see that in the back there's this other matching pentagon that is parallel and congruent. So this is actually a pentagonal prism. Okay, now as for naming edges and faces and vertices, just very carefully count up our vertices. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like there are 10 vertices. As for edges, there is 1, 2, 3, 4, 5. Those are the 5 edges in the front. 6, 7, 8, 9, 10. There's the 5 edges in the back. 11, 12, 13, 14, 15. Those are the 5 edges that connect the front and the back. So there are 15 edges. In a prism, there are always going to be 2 bases. And then there are however many faces we need to complete the figure. So in this case, there are 2 bases, and then there are 5 faces that are attaching those. So that's going to be a total here of 7 surfaces. Now, the reason I'm pointing these out is because I do want to introduce you to something very simple here called Euler's theorem, which showed that in all prisms, in all three-dimensional objects, there is a relationship between the faces, vertices, and the edges. If you look at just these examples right here, if you take the number of faces plus the number of vertices and subtract the number of edges, what do we get? So if we look at this first example with the pyramid, if I take the number of faces, which was 6, plus the number of vertices, which was 6 again, and then I subtract the number of edges, I'm actually going to get 2. Well, what happens when we do that over with the prism? If we take the number of faces, that would be 7, plus the number of vertices, that would be 10, and subtract the number of edges, 15, once again we get 2. Which is what Euler discovered, that no matter what type of polyhedron it is, this relationship always exists. So I wanted to do one last quick one. I'm going to skip this one, but I did want to show you how you could use this. Let's say that I told you we had a solid figure that had 32 faces and 90 edges, and I want to know how many vertices it has. If I use this formula, faces plus vertices minus edges equals 2, always equals 2, and plug in what I know, 32 faces, okay, 90 edges, so minus 90. I'm solving for the vertices. I could very quickly solve this equation and determine how many vertices there are. So if we start with adding 90 to the other side and subtracting 32 from the other side, that should isolate the vertices, and 2 plus 90 minus 32 is 60. So this is going to have 60 vertices. The last thing I wanted to show you is what we call a net. And a net often helps us just to kind of visualize these three-dimensional figures in more of a two-dimensional shape. I always think of it like wrapping a present. So as we look at these three-dimensional nets down below here, I want you to try to visualize what this would look like if you folded it all up and made a shape of it, okay? And then we're going to try to name that three-dimensional shape from that. So if we look at this first one, okay, notice that we have this one, what appears to be a square, or I could just call it a rectangle since I don't know for a fact that it's a square. But notice that all of the other surfaces are triangles. Well, anytime the faces are triangles, which is what we have here, this is going to have to be some sort of pyramid because all these triangles are going to come up and meet at a point. So if I wanted to name this, I would call this a rectangular pyramid, and that base would be the rectangle, and then those faces are all those triangles, okay? The next one you'll notice has circles. Well, anytime we have a circle, this is either going to be a cone or a cylinder. If we have two parallel and congruent circles, then we know that this is going to be a cylinder. But I also want you to notice what shape it is that connects those together. You'll notice that in a cylinder, because we'll get to this later, the surface that connects the two circles is actually a rectangle. Okay, if we look at this next one, we'll see that this is made of all rectangles. But I do want you to notice that two of the rectangles do look a little different than the other four. So these two rectangles, I would say, appear to be more like squares. We don't know that for a fact. But I would say we could call this a square or rectangular or square. And again, this is a prism because we can see if all of the faces are parallelograms, and remember, a rectangle is a type of parallelogram. If all of the faces are parallelograms, then we know it has to be a prism and not a pyramid. And then the last one, again, look for the congruent figures here. We can see that we have this 1, 2, 3, 4, 5, 6. We have this hexagon, and we have another matching one, which is going to tell me that this is a hexagonal prism. So again, these are what we would call nets, and it's basically a flat two-dimensional layout of a